In this video, I'm going to talk about transfer function. So the transfer function it's a mathematical equation. Basically, it represents a system. Okay, so it is a mathematical equation. It represents a system. Another definition for a transfer function is it is the ratio of output response to the input excitation. So as I mentioned, any system I'm going to represent with h of s. That h of s is in the s domain, and output as y of s and input as u of s. So the transfer function is defined as h of s equal to y of s over u of s, assuming initial conditions 0. So assuming initial conditions 0. What are the initial conditions? I'll talk about it in a minute. So whatever this equation h of s equal to y of s by u of s, that is in s domain. If it is in time domain, basically it's going to be u of t and this is going to be h of t. Usually in time domain we'll use the small letters and y of t. So the transfer function is y of t over u of t equal to h of t. That's what the transfer function is. Now, as I mentioned, the transfer function, when you write a transfer function, it's y of s over u of s, right? This transfer function, this h of s, that system does not depends upon the input or output. Okay, this is already pre-made. So basically, when you are building a car is a system, right? That car, it doesn't matter what is your output and what is your input. Car is car. It is made with some other parts. Okay, that's what this h of s represents. Same thing with h of t. Now, this u of t, when it comes to the inputs, there are different types of inputs. One is delta t, also called impulse input. So here you see some inputs, delta t, that's an impulse input. The impulse input is nothing but, usually we don't see that impulse input in our regular life. The magnitude reaches to infinite. Okay, the magnitude reaches to infinite in 0 time. So at t equal to whatever the x-axis is time, y-axis is the magnitude. So this is approaching to infinite in 0 time. Whatever the time t equal to, say that is at the 10th second, the magnitude reaches to infinite and come back. So at 9.999 the magnitude is 0, and at 10.0001 the magnitude is 0. But at that particular 10th second, so if I make that as a 10th second, at 10th second you see delta t as infinite. That input is called impulse input. So for every system you made, I mean, not in this class particularly, but in real life, probably you want to test it, how the impulse response of that particular system, or how the system responds with the impulse input. Okay, this is one type of input. I'm talking about types of inputs. And u of t is called step input. So step input is nothing but, once at t equal to 0, magnitude is going to change to 1. So it's a time, so magnitude is 1. So at t equal to 0, magnitude changes to 1. It will stay at 1. So as a simple example is, once you enter into the room, you turn on your switch. So before turning on the switch, there is no current passing through that wire. Once you turn on the switch, there is continuous current passing through that. That's a step response. Another one is ramp input. It's a t u of t. U of t is nothing but unit step response. So you're going to see u of t everywhere. It's not going to make any difference. So the ramp is, as I mentioned, t. So as time increases, it increases linearly. Okay, that's what the ramp input. And the parabola, which is t half t square, u of t, is nothing but like this. So it's non-linear system for a parabola. Okay, and sinusoidal, we know sinusoidal input. It's look like a sinusoidal. This is input. And exponential, I mean, It might be exponentially increasing or exponentially decreasing. So there are two types of inputs. One is exponentially increasing, another one is exponentially decreasing input. These are the few inputs you can give to the given system to find out output of that particular system. Now the next one is state space equation or state equations. Okay, the state equations basically represents the state of the system. At the same time, basically what we are doing, the state space equation or state equations are time independent quantities. Okay, so what we are doing, we are taking a differential equation. So what is a differential equation? It could be second order, third order, fourth order differential equation. It has differentiations at the same time integrations in that equation. So if you look at a differential equation, now what we are doing, so say if, for example, if you have a differential equation d cube x over dt cube plus 3 times d square x over dt square plus 4 times dx by dt. Okay, so this represents the order of the system. Okay, so it is a third order system. Now what we are doing, and there is only one variable, that one variable is xxx in this case. Now what I'm doing, I'm converting this third order system into 3 single order equations and 3 state variables. You will end up with the 3 different variables. One is x, another one is y, another one is z, or x1, x2, x3, something like that. So why are we doing that? Because solving a third order system might be a little difficult compared to 3 individual first order systems. Okay, first order system. So that's what the state space equation represents, or state equation represents. It is a mathematical model of a physical system as a set of input and output and state variables by a first order differential equation. Let me write down the definition. So the state space equation or state equations are nothing but it is a mathematical model of a physical system as a set of inputs, outputs and state variables by first order differential equation. Now if you look at inductor, capacitor and resistor, we don't have, I didn't draw the resistor here, but here is resistor. First, one important thing, resistor is independent of time. Okay, so the voltage drop across capacitor is I times R. It is independent of the time. Okay, whatever the time is, the behavior of resistance does not change. Okay, here another way of saying it is the behavior of resistor does not change even if it is AC current or DC current. That's what I meant. Inductor behavior changes with AC and DC. So I'm talking about mostly AC. AC means alternating. So it could be any one of these inputs. Look at all the inputs, those inputs, I mean U of t is the only one not changing, but remaining all other values are keep changing with respect to time. Okay, so if you look at any one of those inputs, the behavior of inductor, behavior of capacitor is not the same. Okay, now voltage drop across the inductor is VL equal to L times di by dt. So the di by dt I can represent that as I dot. Okay, capacitor is V of C equal to 1 over C integral of I dt, or I can write this as C times VC equal to integral of I dt, or if I integrate or differentiate it on both sides, C times VC dot. VC dot is nothing but dV by dt equal to I. Okay, this is the current passing through the capacitor, or voltage across capacitor is this is the formula, Vc equal to 1 over C integral of I dt. Now if I have in a circuit, I'm going to draw a simple circuit here. I have resistance, capacitance, another resistor, another capacitor, one inductor. Okay, here is a given circuit. Here how many elements are there? I see 5 elements. Let me label them R1, R2, C1, C2 and L1. Okay. So here we have how many energy storage elements are there. Actually there are 5 elements, but resistor does not store energy. Resistor, it converts electrical energy into heat energy or light energy, so it does not store it. But capacitors and inductors, they store energy. Capacitors store energy in the form of electric field, inductors store energy in the form of magnetic field. So here if you look at this, the voltage drop across this is 1 over C1 integral of I dt, 1 over C2 integral of I dt, and here the voltage drop across L1 is L times di by dt. So if you look at here, I have two integrals and one differentiation or one derivative. So basically this is a third order system. Okay, I can write a transfer function for this circuit. What is the transfer function for this circuit? Y over U equal to H. This is the transfer function of that system. Now our goal is, I'm going to stop this video in a second, but in the next video I'm going to show you how to write the state equations or state space equations for this circuit. Thank you.